Welcome to monochemistry or monobiology, depending on which class you're watching this video for. And today's lesson is all about an introduction to solutions. Now, you should have already been introduced to solutions in previous grades, but this is just kind of like a way to reintroduce the topic and help refresh your memory a little bit. So what is a solution? A solution is a type of mixture called a homogeneous mixture, which means that the substances in the mixture cannot be separated by filtration. So in other words, if I had salt water and I put it through a filter, the salt would not come out. I mean, I'm talking about like filter paper, like a coffee filter. The salt would not come out. And therefore, it's a homogeneous mixture. More specifically, a solution is made up of two parts. You have your solute, which is the substance that is dissolved, and you have the solvent, which is the substance that does the dissolving. And those two things added together make a solution. Now, it's important to note, we often think of solutions as being things dissolved in water. But it's important to remember or to think about the fact that actually solutions are found in various different chemicals and also in all physical states of matter. So you can have solid solutions, you can have liquid solutions, you can have gas solutions. Like air, for instance, would be a homogeneous mixture of different gases. But you can also have mixtures of those physical states. Okay, so carbon dioxide dissolved in water to make fizzy water, or pop would be an example of that. So there's lots of different examples of solutions. Don't limit yourself to thinking about just the water aqueous solutions, even though, unfortunately, that's what we're mostly going to be referring to. But just keep in mind, keep an open mind, and remember that there are different types of solutions out there. Having said that, the easiest types of solutions to talk about are ones that you're most familiar with, which would be ionic substances dissolving in water. Now, ionic substances dissolve most easily in water. And that's because these compounds, like sodium chloride for instance, can dissociate in water, which means it splits apart into its individual ions. I want you to write this down. This is called a dissociation equation. Now, dissociation equations in the future, and I mean the future, I mean for this course, we don't necessarily need to include the H2O. So basically what we would write is NaCl, solid in the presence of water, yields Na plus aqueous and Cl minus aqueous. Aqueous implies that it's dissolved in water because aqueous simply means dissolved in water. So AQ, aqueous, means dissolved in water. So we don't necessarily need to write the water out all the time. It just saves us a little bit of time. If you want to include it, that's fine. Now, the question is, why is water good at dissolving ionic substances? Take a look at the picture that we have here. And there's a couple of things that you need to note or remember. First of all, water molecules are polar, which means, I'll just draw a quick picture here, which means that they have oppositely charged ends. So if we had a water molecule that looked like this, because of the electronegativity difference, and this is something you'd learn in chemistry, there would be a delta negative around the oxygen and a delta positive around the hydrogen. Therefore, they're polar. Okay? So that's important to note. Now, what happens when you put a little bit of salt in some water? The polar water molecules are going to attract both the positive sodium ions and the negative chloride ions in the salt crystal. So here's our salt crystal, and here are our water molecules carrying away our positive and negatively charged things. Okay? The ions are drawn out of the crystal, as shown in the picture here, by water molecules surrounded by them, as you see here, which is called hydration, and carried away. Now, there is a limit to the amount of solute that can be dissolved. There's a limit to the amount of solute that can be dissolved in a solvent. And as you can see, one of the reasons why that is because it takes several water molecules to actually remove an ion. So eventually there's not going to be enough water molecules to do this process anymore. And so therefore it's going to reach what is known as a saturation point. Saturation point is the point at which no more solute can be dissolved in the solvent. It's full of solute. Okay? Now just to really quickly show you here, notice that the orientation of these molecules is so that the delta plus is close to the negative ion. In this piece right here, they're oriented, the water molecules are oriented such that the delta minus, the oxygen part, is closest to the positively charged ion. You should draw this in some fashion. You don't have to draw every single part of it, but you should draw it and label it, and then if you have any questions, it would be easier for me to answer if you bring them to class, because I can't talk to you through the video. Or at least I can't answer your questions through the video. Not yet, anyway. So as mentioned in the previous slide, a saturated solution, which, by the way, is represented here, is when no more solute can dissolve in the solvent. Now, at some point along the way in the dissolving process, as you can see, this is the dissolving process in a bunch of different beakers. At some point along the way, the dissolving process reaches what is known as an equilibrium. And that is represented right here by these arrows. Now, an equilibrium in this state means that the rate of dissolving is equal to the rate of crystallization or precipitation. Okay, so in other words, for every one of these things that's happening, for every one of these that's getting turned into this and this, one of these and one of those is being turned back into that. That's what that means. The rate of the forward reaction is the same as the rate of the reverse reaction. This one representing the forward, undo. This one representing the forward reaction, this one representing the reverse reaction. If those two rates are the same, then you, my friends, have a saturated solution. Now, it is important to note that the solubility of most substances increases as the heat of the solution increases. This allows us, in actuality, to create what is known as a supersaturated solution. Saturated, the word means full of. Saturated solution is a solution in which no more solute can be dissolved. But if we use a little bit of science, we can, in fact, add more solute to the solvent. And how we do that is as follows. Step 1, heat up your saturated solution. Step 2, add more solute. Because the particles are now more spread out, we can add more solute. And when I say particles, I mean the water molecules. The water molecules are more spread out, we can add more solute. If we cool that new solution down very slowly and don't disturb it, we can create a supersaturated solution. When the solubilities of different solutes are graphed at different temperatures, a solubility curve is obtained. And what you see here is a solubility curve for a variety of salts. This is called a solubility curve. Notice that the y-axis is in grams of solute per 100 grams of water, and the x-axis is in temperature, and that should be in degrees Celsius. And each of these salts is represented by a different color. That's important to note. Okay? Now, you should be able to extrapolate some of the data from this, interpret the data from this, and you should be able to manipulate this graph a little bit to see what's going on here. Now, here's a type of question you might get. For instance, at 80 degrees Celsius, which salt has the highest solubility? So what you would do, look around, 80 degrees Celsius, which one has the highest solubility? That would be this one here, which is the red one, Na2HA, so sodium aconate. Nice one. Sodium hydrogen aconate, actually. So there you go. I think probably didn't pronounce that right, but it sounds better when I say hydrogen aconate, right? Anyway, so there you go. That is a solubility curve. We're going to be able to use these. I want you to just jot down. You don't have to draw all the different things, but I want you to jot down what the solubility curve looks like so you have it, and we're going to use this type of curve in class to do some problems. That, in a nutshell, is an intro to solutions, and bring your questions to class as always. These are the references for this video.